Good morning, everyone. Thanks for coming, spending your possibly last or almost last session at Ignite with us learning about networking. We're here from the core networking team in Windows at Microsoft. I'm Greg Kazanta.
I'm Jason Messer.
I'm Dan Kumo.
And we're going to be talking about hybrid connectivity with Windows Server 2019 with a really heavy focus on Azure and what are the things that you need to think about when using Azure, but also using Server and everything in between. So I want to start off by talking about Microsoft's worldview. You may have seen this slide before that basically shows how we position a lot of what we think about with the intelligent cloud being primarily Azure and all the services that run in Azure, and then the intelligent edge, which is made up of all the devices out in the world that are now using this intelligent cloud. Right? You have IoT devices, you have servers, you have buildings that are full of these devices. And really the goal of these things out there that are all around is to be able to use that cloud to do intelligent things, whether it's artificial intelligence or to use some of the new capabilities like serverless functions in there. Well, one of the things about serverless is that it's not actually meaning without servers. You still have servers. They're either running in Azure or you may have these servers running on-prem as well. So you really need to think about more of a real-world view when it comes to connectivity, right? Because you may have a factory that has all these IoT sensors, and when you have a robot that's working faster than the eye can see, it can't go back to Azure every time it needs to make a decision about doing something. It has to be able to make its own decisions locally for these very low latency, these latency-sensitive decisions it has to make. But then it can go to the cloud for things like AI. When do new parts need to be ordered before that robot runs out of things to do? Those things can be analyzed, take a little more time, and take advantage of the what's in the cloud, and don't worry as much about the latency. So when you then think about, well, what are all the pieces of networking? Well, it's not as simple as this big circle with things floating around, right? You may have your main site, which has its own backbone network. All these devices are connected to it. You may have an Azure stack in there. You may have some hyper-converged systems or just other servers running in there. And then depending on how large you are, you may actually have a branch office that has a subset of all that. It's running up there. You may have things out in the field that are connected via cellular, and they need to be able to connect to what you have running on premises. But all these things also need to be able to talk to these functions that are running in Azure as well. And so you have all these cross connections that need to take place. And then the other thing we think about when we think about networking is that it's not just these middle connections, right? It's not just establishing your site to site, which I will talk about that. But you also have to think about endpoint to endpoint. What are the optimizations that need to take place? What are the things that you'd need to do in order to keep the CPU usage at its lowest level for the network traffic so that you have more available for the workloads that are running at either endpoint. And so we're going to talk about all of that. What are the things that you need to do end-to-end to really build an intelligent network for the intelligent cloud and edge? And so we're going to be talking about today about the hybrid connectivity, because that may be what actually brought you here. But we're also going to talk about what are the things that happen at the endpoint that we're doing in Windows Server. Primarily, you'll experience it with your on-premises deployments. But if you remember, Azure runs on server. So a lot of the things that we're doing that you see on-premises with Windows Server, we also do for Azure so that they can use it in their own data centers. So we're going to talk about some of those technologies as well. And then finally, when you connect everything together and you have a truly hybrid network, and you have parts of an application running on-premises, parts of it running in Azure, well, now it's actually important that they actually are in sync together. Because if you have transactions taking place, you want to make sure that the timestamp on a transaction on-prem is as close as possible to the timestamp in Azure. And depending on what industry you're in, you may have regulations that you have to follow. And so we'll talk a little bit about what we're doing around time to make sure that you get the most accurate clocks possible where it's needed. So let's start talking about kind of the middle section, the hybrid connectivity. And so when we think about how do you connect to Azure, right? You essentially have four options. You have public IPs, the most simplest thing you can do. You create a public IP on your VM that you've created, or on a load balancer. And now anything anywhere, whether it's connected through cellular, whether it's in your office, it can connect in through the internet, get to that IP and whatever endpoint is mapped to behind it. That's great, that's its strength, but it's also its weakness, because you don't always want everything to come in through the internet. So they have a number of other options available for being able to connect now more securely and privately. As we start to expand out, there's point-to-site VPN connections, which give you individual server connections or machine connections. Usually it's actually client connections that you connect in from outside into your Azure virtual network. So that's point-to-site, because it's a single machine or individual machine connecting in. But if you have more than a few machines, if you have a whole site or a branch office that has lots of machines that need to connect in, then you'd have to start thinking about site-to-site, because site-to-site gives you that routed connectivity where you can essentially connect as many as you want at one end, and it can route through to connect over the internet into your Azure virtual network. And then finally, you have ExpressRoute. This is your high-performance, low-latency connection with SLAs that are provided by the service provider that provides the ExpressRoute connection to your site, and it's a dedicated line that gives you your direct connectivity to Azure. Now, that is the best option. If you have unlimited budgets, you can connect those to pretty much every site you have, and that's great. But does anybody here have an unlimited budget that they can spend? No? Okay. So you have to think about, well, how do you use the right technology to achieve your goals? So we're going to draw this picture a little differently now, showing which things come in over the internet, which things come in through ExpressRoute. And we're really going to focus now on, because when you use ExpressRoute, Windows Server isn't really in the picture. So we're not really going to focus on that too much, because it's really connecting from the Azure infrastructure directly to your on-premises network, and you're using the endpoint devices that are provided by the service provider that connects that up. Where it gets interesting for Windows Server is when you go through the internet, because we have a number of options there available, primarily through the remote access service and through the VPN client that runs in Windows to be able to connect you either to point-to-site or site-to-site. So I'm really going to focus on those two connectivity options, starting with point-to-site VPN. Now, you normally think of point-to-site as being your way of letting client machines connect in. But really, recently, we've been thinking of, well, what if you have a server? You're a branch office. You have one server sitting there. You want it to be able to take advantage of other machines or even services like Azure Files that are running in your Azure virtual network. But you don't want to set up a full site-to-site endpoint on there, that you have to have an appliance that's running and doing all of this just for one machine or a handful of machines. And you're certainly not going to pay for an ExpressRoute circuit to go all the way to there. So as we've been thinking about over the last year or so, we've kind of realized, well, point-to-site is actually not a bad option for this case. If we can create a connection that's persistent, that is easy to set up, then actually you can use that for connecting some of these machines to your Azure virtual network. And so really we've been focusing on making this as easy as possible. And combined with the Windows Admin Center, we figured out we can build in an experience that makes it very easy for those of you with relatively small offices or individual offices. You may not even have an IT department that you have available to set up complex routing and networking. So we built into the Windows Admin Center this concept called the Azure Network Adapter. And really what it is an easy way for you to set up a point-to-site connection into your Azure virtual network. Even if you haven't actually set up your Azure virtual network for gateway connectivity yet, the Azure Network Adapter will do that for you and walk you through it in a way that's very easy so that pretty much anybody can do it. It takes care of configuring the Azure Virtual Gateway if you haven't done that yet. It goes in and queries against the Azure, the virtual network that you select in the Admin Center, and goes in there and will give you the options to connect that. It handles all of the certificate management, creating self-signed certs, putting them into Azure, putting them on the client machines, so that you don't have to do that. I mean, if you've gone through the Azure documentation and followed their step-by-step guides, there's a lot of cert creation in there, and dealing with that is not always easy. So we've done that for you. We then set up the connection to be as persistent as possible given the technology that's in the box in Windows Server. We set it up to be persistent, to be established by the server that's establishing the connection, and being able to auto-reconnect as needed if that connection does go down. And we also want to make sure that even if you're not logged in that machine, that connection stays up as well. So let's actually go through and take a look. Now, how many of you have seen seen a demo of Azure Network Adapter earlier in Ignite, either from Jeff Woolsey or, okay, good, a few of you. I'll try to go into a little more detail than what he did. So here's my Azure account. You can see I have a VM, a virtual network. It's in the West US region. And I'm going to go and I want to connect just an individual machine to that. So here I am in Admin Center. I'm connecting to that server that I want to connect into this virtual network. And this is your basic admin center view of all the properties of that server. I'm going to go to the network. And you can see here I have a single adapter. It'll come up in a second. It's a virtual adapter because this server is a VM. But this works not just with VMs. This could be a physical machine as well with a physical adapter. And so I'm clicking on Azure Network Adapter, and it already authenticated with Azure using the connection that's already been put in for other services as well in Admin Center. And you can see it's connected in, and it pulled up the list of regions. I'm selecting the US West region. It's populated now the set of virtual networks that are in that region. We have deep links. If you click on that, it'll take you directly into, I'm going to pause this for a second. It'll take you directly into the virtual network that you've selected so that we don't want to recreate the entire Azure experience in Admin Center. We want to be able to deep link in there to get you there so that you can then do the more advanced things directly from Azure. But for making things easier, we do that through the Admin Center. So you can see here as well, we have the properties of the virtual network gateway. We've detected this virtual network actually has a gateway subnet already created, so we basically populated in what was already set on the virtual network. If it wasn't already set, we would give you the ability to put a new subnet in for the gateway. We let you select the gateway SKU to depend on how much bandwidth you need. Of course, this is where you will actually start to get charged money based on which type of gateway you select. Here we have the lowest cost gateway 1 option. And then finally, you have to give a client address space for what are you going to connect to. Now, we do by default do auto-generated certs, but if you do create your own certs, if you have a CA and you do want to do that level of management, you can go in and populate with those certs as well. So you hit OK, and actually that's it. It's going to go out and do, from this point on, do everything else that you need to do. It takes about 35 minutes, so I've sped up some portions of this. But here you can see within Azure, it's already created the gateway. It's in the updating state. This is the part that takes 30 minutes for it to actually create that VM. But you can see here it populated the address pool that I defined for the client. It set up the connection type. Here's the cert that it created and put into Azure for you. So you didn't have to touch any of that. So we'll go back, and again, it takes about 35 minutes, depending on how Azure feels that day, before it'll actually come up. And you'll see some pop-ups come up in the right corner. So the next thing that'll happen is it'll say, it's finished creating the virtual gateway in Azure, because basically Azure has to provision a VM to do that. While I was recording this, I got a little impatient, hit refresh a few times. There it is. It came up saying the Azure Virtual Network Gateway was created. So now the Azure side is done. Now it's going and configuring the client for you, because normally when you create a VPN connection, you have to go to Azure, download the client, install the client, take care of your certs, and then your connection comes up. This does that for you as well. So this takes about 2 or 3 minutes. After that's finished, you'll see then a new connection come up in the network panel here. This last part now, if you add additional machines, you want to add another machine to this Azure Virtual Network, you don't go through the full 35-minute part. You just go through the last 2 minutes. Now it's finished. It basically said, or actually it's almost finished. And you only go through this last part. It takes about 2 minutes then to add additional machines to this virtual network. There it is, the point-to-site connection. If you select it, we have details that you can bring up on the bottom. Again, that'll bring you with, again, a deep link into the virtual network. That will bring you directly to that Azure page for that virtual network if you need to know what your properties are. Here you can see if you go to ipconfig of the VM itself, this is the server that we set up. You can see before I created the NIC, there was only one adapter with a 247 address. After adding in that VPN client on this server, I have now a 10.2.0.2 address. This is now in the address space that I defined. If we look at the route table, you can see that the virtual network address space is in here. The 10.1.1.0 subnet is going to my virtual network, and it points across that 10.2.0.2 link. So any traffic that's destined for the virtual network will go across that link. And so I'm going to go into my virtual network next. I'm going to actually start my VM that I have in the virtual network because it's not running yet. And then we'll start a ping and see that the traffic's going through. So here I go back into Azure. I'm going to find my VM. So it's my AD VM that I'm going to start up. Just scroll through and find it. There it is. And I will hit start on it. There we go. Now it's going to be up and running. Excuse me. This will take a minute or two to start. And when it does, we're going to go back to the server that we set up with the VPN connection. And we're going to start a ping. Well, in order to do the ping, we have to know what the client address of this machine is. So quickly go over to the networking panel here to see that address. There it is in the top right on the 10.114, 10.1.1 subnet, but it's 10.1.1.4 is the address. So we're going to go back to our machine and show that we have direct connectivity to it as if we were directly connected and part of this Azure virtual network. So here we go. We're going to start the ping. 10.1.1.4. Machine's still starting. We're going to make it persistent. So while we wait, because I didn't know how long it would take for the machine to actually boot. And there it is. It booted up, and now we're actually able to ping it. We're directly on that virtual network. So that's great. So that's Azure Network Adapter. Really easy to connect a point-to-site connection. But really, eventually, you may get to a point where you have too many machines that you want to connect through point-to-site, and then you go to site-to-site. And we provide the remote access service in Windows to be able to give you that capability to do that using Windows on premises. It comes as part of standard Windows Server, so most of you that have Windows Server licenses have that available. And there are a few different options for deploying it. You can deploy it so that it connects directly to your network, being your edge gateway. If you have an Azure Stack uses it internally to connect to your virtual network, so you can connect Azure Stack directly to Azure. Or you can even, if you have a hyper-converged system, if you're running Windows Server SDN, you can connect directly from Azure, from the remote access there into your virtual network. Now, in Server 2019, we haven't really changed much of the functionality in remote access in a while. Same remote access you've known and loved for a long time, but we've been working really hard to improve the throughput. In the cases of SDN, where we can take advantage of hardware offloads, for IPsec VPNs, we've actually improved the performance by 3 times. You don't see quite the same level of improvement when you're running remote access standalone, but here's a comparison of a single connection. IPsec on top, Server 2016 are the 2 short bars on top. Server 2019, the dark blue bars when you're running remote access just standalone, as your gateway endpoint. For a single connection, you're getting almost 1 gigabit per second. When you're running it with SDN, you're getting almost 2 gigabits. GRE tunneling, we've made similar performance improvements. When you actually take the aggregate, because that's generally, you'll have more than one TCP connection, then you can see the performances improvements are even greater. About 50% for standalone remote access, and almost 3 times for when it's used as part of an SDN system. So Azure Stack will eventually be able to take advantage of this when they start to ship Server 2019 internally. You'll have it available though with your server deployments today. So that's it for hybrid networking. Now let's work out from the bubble to think about what happens when you get more closer to the edge.
Morning, everyone. So I'm going to talk about host networking and server networking, high-performance server networking today. Host networking represents kind of a new frame of reference, especially with the introduction of containers and nested virtualization, where we actually have a whole subset at times of a network on one particular host, and the containers or VMs are connecting into that. We'll also talk about server networking and the high-performance network data plane with technologies that are being introduced in Windows Server and also being brought to Azure for Azure-optimized networking connectivity. So what else do we need from this intelligent hybrid network to connect the pieces from the intelligent cloud to the intelligent edge? We need some basic principles like reliability. We need to make sure that our connections are stable, won't go down, that we have consistent performance. We have consistency in the way things work, in the user experiences that we expect our users to have both on-premise and in Azure, and also from a performance perspective. They get the same performance benefits that they get either on-premise and Azure. So that's some of the key principles that we're working with when we're introducing these hybrid type network connectivity features. We have a ton of shared innovation and features that we do between the Azure Public Cloud and Windows Server. As you know, and as Greg mentioned, Windows Server is what powers the Azure Public Cloud. And so all of these technologies that we're bringing to Azure are available in Azure. We're also taking them and putting them on-premise in Azure Stack deployments or SDDC clusters or branch offices, what have you. We're doing the same thing with the things that we do in the Windows Server core networking team and driving those performance improvements into Azure itself. One of the ways we're doing this is with containers. I don't know how many are you familiar with containers. There's been quite a bit of buzz of containers recently, more from an application developer's perspective. where folks are moving away from the traditional 3-tier app logic towards more of a microservice-based architecture, potentially doing what we call a lift and shift, moving the workloads that were running in a VM, packaging them inside of a container and redeploying them, and then having the ability to easily scale those out. And so again, these still use a lot of the primitives in Windows Server, both on-prem and in the cloud, specifically for container host guest VMs. Again, the container host could be running bare metal, but most likely it's running in a guest VM somewhere, either in Azure or on-premise. We have two different types of containers that are kind of alluded to here on the right bottom hand of the screen. One is the Windows containers, which uses just process isolation. It still uses the same Windows Server kernel. It's just doing process isolation boundaries to make them their own unique entity. We have a more stringent security boundary that we enforce using Hyper-V isolation with Hyper-V containers. And we're actually working on this for not only Windows Hyper-V containers, but also Linux Hyper-V containers. With container networking, you have a lot more flexibility in how you do service discovery, saying I need to access the web service or the database service. It's dynamically load balanced across the host and across all these different instances of container instances backing that particular service. What we do with containers in particular now is not just limited to a dev machine, but obviously we want to run these in production. And to do that, we need some sort of an orchestration or scheduler mechanism. Now, the most popular one that you've probably heard a lot about recently is Kubernetes. That is what Microsoft is really focusing on, and we're wanting to make sure that we have all the networking support and primitives needed to work with a Kubernetes cluster for our Windows containers. We do that through something called a CNI plugin. It's the Container Network Interface plugin. And it supports different types of topologies and environments that we're running in. And so you see here a list of about 5 or 6 of the different networking CNI plugins we support and the different topologies they're used for. Most noticeably, obviously, we use Azure CNI. And so we have the Azure CNI plugin that allows you to connect your containers to an Azure virtual network. On-prem, we usually recommend Flannel, which is another CNI plugin. You can do either a host gateway mode to do routing between the nodes and the pods in that particular cluster, or you can do an overlay-based approach using VXLAN encapsulation. And we have a few more. The interesting thing about containers is it actually has a few different network segments. We have this thing called a cluster sitter, also a management network and a service sitter. Now, a cluster sitter is really what connects these individual containers or pods to a network. You can think of a pod, this is more of a Kubernetes construct, but you can think of a pod as a resource boundary where you can have one or more containers running in that. And you have different resource utilization from CPU or disk usage or sharing the same network namespace. All of those are inside of a pod. So you connect your pods or your containers to this cluster network. And then those pods actually have to obviously have to get connectivity to the other pods across the cluster in different nodes. And so we use the management network to do that. Lastly, we have something called the service sitter. Service sitter is basically a service range of virtual IP addresses or VIPs. So instead of having to go to one particular instance of a pod that's providing web service, for instance, you just go to the virtual IP address, and it automatically load balances across that virtual service sitter network. One thing I'm really excited to introduce today and announce is support for network policy enforcement with containers using Tigera Calico on Windows. Tigera is a market leader in the space of network policy and has really written the definition for what ingress and egress security policies look like in Kubernetes. And so we've been partnering closely with that customer, and we're happy to announce an early adopter TAP program for anybody who is interested in actually providing not just network connectivity, but also network security for ingress and egress. So I want you to take away from this, we have flexible container networking both on-premise and in Azure for hybrid to do easy load balancing, either for lift and shift of your existing workloads running in VMs moving to containers, or re-architecting and building new applications using microservice-based architectures. We have a number of different offerings to actually help you with this, so it's not you're just doing it yourself. We actually support things like Service Fabric, Docker Enterprise Edition, vanilla, just plain upstream Kubernetes, and Red Hat OpenShift, which is now in preview. So you can start on-prem, and then you can move, or you can start in Azure. We have services like Azure Service Fabric, and also Azure Container Instances. ACI is built on top of Kubernetes, as is the Azure Container Service for Kubernetes, ACS. We also have a few other offerings that are in preview, Azure App Service and Service Fabric Mesh, all to provide a hybrid experience for containers. So you can build your containers on-prem, and then you have an easy way to migrate them into the cloud. We also are partnering, and this is one of the things I'm really excited about, is it's not just Microsoft doing this work, but it's actually a whole community of companies and open source projects we're working with to deliver this. So we're checking in code in upstream open source repos with Kubernetes and OpenShift and Docker and Calico with Tigera. So a lot of exciting things happening there. I want to give you just kind of a quick demo about what this actually looks like. So again, I mentioned that pods are kind of the isolation boundaries for particular resources. They are typically running one or more containers inside of them. And so this is an example basically on a single node, but it could be across multiple nodes in a cluster of a few different pods to which we want to apply network policy to. And so we took up the Minecraft theme of having different types of factions and classes of these things. So we have, kind of the hostile faction, zombies, and then we also have a faction of friendly forces. Lastly, we have then different classes or types of objects, whether it's a player or a base or something else. And really, we want to be able to limit communication, obviously, between these two. Just by default, they all have communication and they all have connectivity with each other. And so what we're wanting to do is build some sort of network policy enforcement to block connectivity between the hostile and the friendly factions. And so in a minute here, you'll see the video actually showing how we do this. And I might need to speed it ahead. So we're only wanting to have the friendly factions between the player class and the base class be able to talk to each other, and then have all other communications between the hostile parties blocked. So let's look and see how we do this. Go ahead and zoom ahead here. Oh, that did not work. Excuse me a minute while this video is playing. Just for the sake of time, honestly, I think I'm going to skip through this. But what we are going to be able to show with Calico is how we actually define that network policy and then block communications between it. Moving on from containers, that is a hybrid play, obviously, where you have containers running in on-premise environments and also in server or in Azure. But we also have a lot of improvements with our accelerated networking data plane. We have a few different types of offloads and optimizations we do. Some are very software-centric, things that we do in something called the synthetic data path between the network card through the vSwitch and to the VM network adapters themselves. We also have things we do through what's called the IOV, SRIOV data path, which completely bypasses the virtualization host. The reason we do that is we want to dedicate more CPU resources and memory resources for actually processing applications and workloads running in those VMs on the host, rather than having them busy just doing network level processing. And so we have a few different combinations of what we do here. One of the things that I'm really excited about is dynamic VMMQ. Now, we've had a long journey of providing different spreading support across different logical processors, different queues with VMQ or VM multi-queue using physical NIC resources. But it's been very static configurations in the past. And so you've had to really understand what your workload looks like and configure it to be running on specific queues. And once those queues are set up and running, they don't tend to move. They're just kind of pinned. So what we've done with dynamic VMMQ is we are able to load balance across multiple queues or logical processors. When there's additional load coming into the system, we can expand across the number of queues and the cores that they are attached to better handle that workload. And then when we're actually getting to a static state, we're wanting to coalesce and only process those workloads on a single queue or on a single logical processor, and have the rest of the logical processors able to process tenant workloads. So it's very responsive to tenant workloads in this fact. And so I want to kind of show a quick demo of this. And what you see here is we're going to be sending and receiving traffic. In the bottom left-hand side, you see a graphical map of all the different VM receive queues, and they're right now spread across a number of different processors. So you can see the green one, the second one in from the left on processor 10. You can see also the light blue one, about 6 or 7 more in, that's also on processor 10, but they're all spread across and kind of parked on these logical processors at the moment. So we're going to go ahead and start the process of the network traffic processing. You can see all of a sudden they are all hitting, and what they've done very quickly is they've coalesced onto one particular CPU. And so now they're all running on, looks like CPU 17 and processing that network traffic. So this is really cool. So we've hit this hard. It's coalesced onto one particular processor and allows the other processors, logical processors, to be used for the application workload itself. When that traffic is done being sent, then it goes back to kind of a static distribution of, or a static park of where those queues are actually on the logical processors. They're spread across so that they can quickly come back up again whenever needed. One thing we didn't show in this demo is also if you have a high intensity CPU resource bound workload running and it's starting to use resources on that particular logical processor where the queue is processing the network traffic, it can actually move that to a different logical processor to make it optimized for the workload itself. So we're really excited about that. Another really cool feature that's being used both on-premise and coming soon to Azure is receive segment coalescing, RSC. So this is a rather older technology actually that's worked for native hosts for quite some time, but now we've made it work for virtualized environments with the vSwitch and also with VMNICs itself. What it does is it takes a number of smaller packets that are received on the wire, and instead of processing those individually one by one and all the overhead that's incurred from that, it coalesces all those packets into one. So they all can have the same IP header essentially, and then the payload is coalesced into one packet. And then that is the one that's actually presented to the vSwitch and the VMNICs themselves. This gives huge performance benefits for literally no cost. And so what I want to show you here is a demo of RSC in the vSwitch. So right now, by default, we're going to be sending traffic again, and you can see in the bottom hand of the screen that RSC, software RSC in the vSwitch is disabled. So we're going to go ahead and start running traffic, and you can see in our VM we're getting quite a bit of throughput. I mean, we're getting 37 gigabits per second. That's awesome, just right there. But it's using up 44% of the virtual CPU in the VM itself. On the host side, it's even worse. It's actually using up 68%. This is before any workloads are running. This is just doing network level processing. So now we're going to enable this new software RSC feature. And we'll see that we get the same amount of throughput, but for much less of the CPU resource utilization. So it dropped about 10% on the host and about 10% on the virtual CPUs as well, just by enabling that one switch. This is actually enabled by default whenever you create an external vSwitch, and it just provides a great number of performance benefits from a latency perspective by decreasing the CPU utilization, and also from a throughput perspective, able to get higher throughputs. The last feature I want to talk about in the data plane is guest RDMA. Now this is an improved feature. We had limited support for this in Server 2016. But again, our goal is to offload the host CPU as much as possible. And one of the ways we did this, which I mentioned previously, is with a technology called SRIOV. In SRIOV, you have a virtual function that's running within the guest VMs themselves. And you have a physical function that's actually running on the physical NIC, but it's bypassing the virtual host in the Hyper-V virtual switch. Now, there's positives and negatives to this. The positive is you get much better performance with lower latency. The negative is you lose some of your ability to enforce network policy as you traditionally did in the vSwitch. And so for right now, we're recommending this be used in trusted workloads, meaning that we're assuming that this workload, whether it's an SMB file server or SQL server, is behaving as it should, and it's not going to be competing with resources across other applications running on that host or on the fabric. But we're continuing to do more and more work here, and you'll see this space improve with enhanced policy support in the future. These two features I really want to call out. We've done a lot of work with the open source community to make sure they run not only for Windows, but also for Linux on a Hyper-V host. So Windows and Linux both get the benefits I explained earlier about RSC, Receive Segment Coalescing, and also this guest RDMA. And we have check-ins pending in the upstream Linux kernel distro to make this work in the Linux kernel. Now, the individual distributions may take a little bit longer before they get those changes into their distribution, but upstream, these will be available in the next week or two. So we're really excited about having that support for both Linux and Windows. And this is being used in Azure also. So a lot of innovation, a lot of features that we're sharing across the board. Another cool thing we're doing is something with video broadcasting. I don't know how many people are familiar with video broadcasting. I wasn't until just recently, but we've been working with Cisco and Intel actually on a project that involves a transition from the older video broadcasting industry, which used an interconnect fabric called SDI, Serial Digital Interface, and they are moving actually to an all IP Ethernet-based network and doing a lot of virtualization. Now, with higher and higher quality streams of 4K and 8K, we need to be able to scale up. Now, the problem that Cisco had with their existing library, which is called VMI, was that when they used the Windows networking kernel stack, it actually had too much latency. There wasn't enough throughput available to push more than about 5 HD streams across, and they could only get about 8 gigabits per second. So even if they had a 40 gig NIC card or a 100 gig NIC card, they were still bottlenecked by the host kernel networking stack itself. And so what we've done is we've introduced something that actually began the Linux community and is available in Azure, and we're bringing to on-prem called DPDK. Data Plane Development Kit is for user mode fast packet processing. Just like SRIOV bypasses the virtualization host, DPDK bypasses the networking stack in the host. And so it gives user mode applications like video broadcasting direct access to memory regions on the NIC card itself. And so this is just super efficient, high throughput, low latency speeds that we can drive through here. We showed this at a DPDK summit in California about a few months ago and showed 70 million packets per second. So really saturating the link with those small packets. But to put that into perspective from a video processing capability, with DPDK, we can now saturate this 40 gigabit per second link with 25 HD streams. So we've had a 5x increase just by using DPDK on Windows to do video broadcasting with Cisco. And as standards increase from 4K to 8K, we'll be there to be able to scale up with it. This is going to be an open source library that Cisco is going to publish, and we're looking for other customers who will then use it. They've had a successful demo and a lot of traction at a recent video broadcasting conference called IBC, and we're excited to see where that goes. But not only just video broadcasting, we're also wanting to use DPDK for other things, whether it's like an NFV appliance, like a load balancer, or a firewall or something else of that nature. There's a lot of benefits we can get from DPDK. This is just one example. Just to make it real, this is basically showing kind of a very, very simple, rough demo about what it's doing. But on the top left, you can see this VMI demux module receiving RTP. RTP is usually what media is streamed over the internet with for video and audio. And all these packets are being processed via DPDK and exposing them as video frames. If you move then to the top right, clockwise around, you have a VMI adapter module, which is routing these video frame streams to a converter. Bottom right-hand side, you have this 10 to 8-bit converter to make it in the right format. And then finally, you have a VMI adapter module that's routing and dispatching this video according to the number of outputs. So right now, it's actually broadcasting just this simple video, H.264, or 15 frames per second. But this is just to show, hey, this is actually real. Cisco is demoing this. We're going to open source it soon. using DPDK to scale up to 4K, 8K streams and saturate those links for this huge transition that's happening in the video broadcasting industry. One last thing I want to talk about is LEDBAT. LEDBAT is a latency-reducing, non-interface congestion control. A lot of fancy words to basically say that what we want to do is preserve throughput and latency for user mode applications or applications that are currently running in the forefront, and deprioritize at times some of the background transfer. So whether it's like Windows Update, sending you a bunch of data to update the systems, or some other low priority flow, we want to be able to say, you know what, we really don't want that to suck up all the throughput or use up all the CPUs so that our other user mode applications are suffering for that. So what we do is we have kind of two axes we look at this at, bandwidth versus time and latency versus time. What we have, I'm just going to skip through these, but basically it shows that as the bandwidth increased, we have these high priority flows, and if a high priority flow comes up while we're also doing a low priority flow like an update service, we're going to give less bandwidth to that low priority flow and increase the amount of bandwidth we give to the high priority, the active user flow. And the same thing, we do this with latency. If you had a low priority flow like an update service running and it was providing these updates, it would actually take up a lot of the CPU processing, so the system was really unusable. And so we want to make sure that LEDBAT keeps latency within human tolerance so people don't lose access to their systems. And so we can do latency protection with a LEDBAT-enabled workflow to make sure it takes up lower CPU costs, lower CPU utilization, so that your higher priority flows get the CPU resources they need. So I'm going to quickly now turn it over to Dan Como, who's going to talk a little bit about high accuracy time.
Thanks, Jason. All right. So I'm sure if I took a quick poll, most of you have deployed Active Directory. Pretty confident in that. And if you deployed Active Directory, you're no doubt aware time clients, they synchronize first to domain controllers. Those domain controllers synchronize to your PDC emulator. And on premises, everybody's happy. But now you're trying to lift and shift some of your workloads into the cloud. And now you have some decisions to make. Where do your time clients sync time from? Do you deploy a domain controller in the cloud so that they can sync within the Azure Virtual Network? Or do you have them sync over your site-to-site VPN or Azure Express Route, as Greg was talking about earlier? And so you have some of these challenges you have to overcome that only come up when you have the cloud here. This is very similar to having cross-site scenarios, but you're not in control of the Azure hypervisors. And so you have to consider these. And so our generalized pro tip here is, well, rely on a common data source, right? UTC is, common, right? Everybody knows what UTC is. We all agree what UTC is. So in Azure, we kind of take care of this for you, right? So if you synchronize your workload to Azure through the Hyper-V vMIC, what we call the virtual machine integration component, you'll get time up to a UTC-accurate clock. And now all you really need to worry about is your on-premises systems. And so to help along with that, we've done a lot of work to actually bring higher accuracy time. And this may be whether you're using Active Directory in the cloud or any other workload, including financial services, which are now requiring extremely high accuracy, high precision clocks. And so very quickly, let's just run through some of the interesting work that we've been doing. So precision time protocol, I want you to think back to the last thunderstorm you've actually been a part of. Did you see the lightning at the same time that you heard the lightning? Typically no, right? And so besides the speed of sound versus speed of light difference, you also have a number of things in your way that's actually introducing latency in the sound. Maybe you have a bus running by, honking its horn. You have buildings in the way. You have houses. You have trees. You have all these things that add latency between that sound. And likewise, on the network, you have other things that interfere with your time. So you have switches in the way. Each switch, each router, each firewall, they add latency. And they add, it makes it harder to actually make sure that you get the right time at the endpoint, at the time client. And so Precision Time Protocol is a new network time synchronization protocol that we have on Windows. We have a time client on Windows for PTP. And this allows the switches to actually participate. So as the time measurement comes from your time source, the switches, the routers, the firewalls, whatever supports PTP, can insert their measurement into, insert the latency that they've added into the measurement and continue that packet on its way until ultimately to your time client, thereby eliminating the latency that they've added. To go along with that, the last mile here is the Windows networking stack. And so we've brought software timestamping that sits at the NDIS layer, and we'll take a timestamp when a packet comes in and when it leaves the networking stack a little bit above that, and that will also remove the latency that's introduced by Windows. And you may also be noticing this very funny clock here down in the bottom. You can see it actually right now just hit number 60. This is not a bug, okay? If you're in a financially or highly regulated industry like the financial services market, healthcare, pharmaceuticals, power and energy, et cetera, you may have to actually worry about leap seconds. So quick show of hands, who knows what a leap second is? All right, that's way better than I expected. All right, so basically the background here is that the Earth's rotation is slowing, and UTC is based on atomic clocks. So those atomic clocks are very accurate and precise, and they keep time way better than the Earth does because the Earth is slowing down. And so when they diverge far enough, we actually insert a second into UTC in order to, well, we don't. Microsoft doesn't, it's not our fault. But there's a second inserted into UTC. And so if you're in one of these regulated industries that have extremely high accuracy time requirements, less than a second, you need to worry about this because this one little second, this one tiny measly little second can put you past your time dependency. And so in Server 2019 and also on Windows 10 clients, we'll have support for leap seconds. And as you can see there, what will happen is you insert the 60th second. Now, it's not just important that you insert that extra second. It's important how you insert that extra second. And so there's a very common approach called smearing. This is something that we don't do, actually, because it's not compliant with the regulated industries that we're working with. You have to put that last second in at the last moment, the 60th second. You can't just smear it out throughout the day. And so that's going to be available both on Windows Server 2019 and Windows 10. And of course, we just released our top 10 networking features in 2019. Many of these do apply to Windows 10, but it kind of covers everything we've talked about today. The intelligent edge and the intelligent cloud, site-to-site VPN. We have all of these pieces on premises and in the cloud. And please go to our blog, check out the features here. We have videos, we have validation guides. And of course, give us your feedback. Let us know if you have any questions. You guys, anything?
All right, so with that, thank you for attending. These sessions have basically already happened, but we have a number of links that you'll find useful, primarily the one to the networking blog on the bottom right. We also had an SDN session early yesterday that you can go back and watch. We'll leave this up in a second. Before you finish up, please fill out your evals, let us know what you thought of this session, and have a good trip home. Thank you.